Okay, so looking back at column 3, which is the sampling distribution of the means, this was all the possible sample means for samples of size 2. Let's calculate the mean of these means. Okay, so these are all possible sample means. If we put these values into our calculator, into a calculator list, and calculate the mean of these values, what we are calculating is basically the mean of the sampling distribution of the means. I know it's a mouthful, but really it's simply the mean. Basically add them all up and divide by the total of this collection of numbers in column 3, the sampling distribution of the means. So if we go to our calculator and we put in, let's go, and I'm going to put into L2, okay, see, we're going to put in all the possible sample means. Okay, and there should be 10 rows. After you have all the sample means in there, find the mean of the means, which is simply, let's find the mean of that column, L2. So 1var stats, change the list to L2, and calculate. Okay, and notice that the mean of L2 is 68. Now that 68 should be familiar because that 68 is the same value as the population mean. So if we go, take a look, okay, it's still 68, which is the same as the population mean. Now that isn't coincidence. That's always going to happen. If you take samples of a population, all the possible samples of a particular size, in this case size 2, and you find the sample means, and then you find the mean of those sample means, you get the same value as the mean of the population. Every time, this will always be the case. The mean of the sampling distribution of the means has special notation. So what we just calculated, basically summing up and dividing by the total all of the possible sample means, is denoted by mu sub x bar, and this is how we write it. Mu with a subscript x bar. It indicates the mean of the sampling distribution. The mean of the means, the mean of the sampling distribution of the means. And by definition, mu sub x bar, the mean of the sampling distribution of the means, is always equal to the population mean mu. So there's really little to no calculation. If you know the population mean, then you know what the mean of the sampling distribution is. Okay, again, there's column 3. Let's calculate the standard deviation of this data set. So we're going to go back to our calculator and we're going to put the data in a list, which it already is, and we're going to look at the value for the standard deviation when we run 1var stats. This is basically the standard deviation of the sampling distribution of the means. Now when we run 1var stats, we'll have 2 possible standard deviations to look at. We are going to look at the population row, standard deviation for the population, because these numbers represent the entire set of all the possible sample means. So we have all of them. We're not sampling them. This is all of the values, so we're going to look at the population standard deviation. So if we look at the calculator, and here's that output. I didn't delete it from before. We found that the mean of the sampling distribution of the means was 68, and the population standard deviation sigma x is 18.5418. 18.5418. Okay, so our standard deviation of the sampling distribution of the mean comes out to be 18.5418. And it has special notation. Its notation is denoted by sigma sub x bar. So where the population standard deviation is sigma, the standard deviation for the sampling distribution is sigma subscript x bar. So that little x bar down there tells us that we're dealing with a sampling distribution. This is the standard deviation for the sampling distribution. The standard deviation of the sampling distribution is a measure of how spread out the sample means are from mu. Okay, so we remember that a standard deviation basically tells us how spread out or clustered data values are. So if we measure the standard deviation, it gives us an idea of how far these values in the sampling distribution are from the population mean mu. The standard deviation of the sampling distribution of the means, mu sub x bar, is also known as the standard error. A lot of times saying this is a mouthful, standard deviation of the sampling distribution of the means. Because it's such a long-winded term, we often abbreviate it by saying the standard error. Now that's different from the sampling error that you calculated and you put into column 4 of the chart on the handout. Standard error is different from a sampling error. Standard error is the standard deviation of the sampling distribution. The standard deviation of the sampling distribution will always be smaller than the population standard deviation sigma. So if you take a look at the value that we got for sigma earlier, and now the value that we're looking at for sigma x bar is smaller than sigma. So our value for sigma x bar, the standard error, came out to be 18.5418. The value that we got for the population standard deviation, which was simply those 5 commuters, when we put those 5 commuters into a list and we looked at their population standard deviation, that was 30.2787. So notice that our sigma x bar is less than sigma. The larger the standard error is, the more dispersed the sample means are from the population mean. Okay, so if we consider the fact that our sample means are possible sample means of size 2, if we have a standard error that's large, it means that those sample means are spread out far from 68, our population mean. On the other hand, if our standard error is smaller, then it would mean that the values are closer to the population mean. The sample means are closer to the population mean or clustered. Okay, so there are some sample means that are closer to the true population mean than others. So we already saw before that when we had a value of 67, our sample mean of 67 was pretty close to our population mean 68. In fact, its sampling error, which was simply found by taking 67 minus 68, which is -1, it has an absolute value of 1, which means it's only 1 unit away from the population mean. But others are pretty far away. So 44, which is also a possible sample mean, is far on the left. 85 is on the right. And notice that the location of each of these possible sample means is at different points on this horizontal line. Okay, so at the farther ends, we have a sample mean of 43, and on the other side, we have a sample mean of 102, both of which are far from our population mean 68. And close to 68, we have 61, 67, and 66. Taken together, all of these values have a standard error. Okay, they don't each have an individual standard error, rather that each of them, when taken together, have a single standard error, and that came out to be 18.5, whatever it was, 18 point, 18.51, let's see, I can't remember. Standard error came out to be 18.5418. Okay, so the distance from mu equals 68 is called the sampling error, which we already calculated. Is just simply taking x bar and subtracting mu. For any distribution, the standard deviation tells us how the values deviate from the mean. So that we saw that with distributions earlier in this course, and now we're seeing it with distributions here, a sampling distribution. When we calculate the standard deviation for the sampling distribution, we get an idea of how spread out data values, or in this case sample means, deviate from the center, from the mean. In a sampling distribution of the mean, the standard deviation, which is the standard error, tells us how the sample means deviate from the population mean mu.